Hello everyone, my name is Jawad Tahir and today I will be presenting my ongoing research which is titled Streams Under Test, Performance, Correctness and Recovery Study of Stream Processing Systems Under a Range of Failures. Now let's first build a motivation that why are we benchmarking distributed stream processing systems. As we know that the data volume and the velocity are increasing every year. For example, here it's shown in the graph which shows the data volume reduced per year from 2010 to 2025, and we can see that the data volume trend is increasing exponentially, whereas the processing power to process this huge amount of data is being stagnant, as shown in this graph, which shows the performance upgrade from the previous year model, and we can see that the performance upgrade is hitting a plateau. So what do we do? To process this ever-increasing data, we create a network of machines where the processing is distributed in the network, and if we want to process more data, we just add more machines to it. Now let's see why are we benchmarking in fault tolerance capabilities. Failures are inherent in any distributed systems. As stated in CAP theorem, we can only choose between consistency and availability under network partitions. And these failures can cause catastrophic damages, such as data loss, data duplication, incorrect results, and performance degradation. Beidou also reported to have more than 290,000 faults in their infrastructure in 4 years, which equates to about 200 faults in a day. And we also conducted a survey of this failure and their reasons, and we found the faults which causes these failures. Now let's do a bit of background on distributed stream processing system. Distributed stream processing system process the unbounded data. For example, a stream of tweets or a stream of clicks or a stream of taps or the sensor readings. DSPs provide us real-time insights such as trending hashtags or trending videos, as opposed to distributed batch processing system which only provide us historical insights. A processing in a DSPS is defined by a graph of operators. An operator can be of two types, either stateless operator or stateful operators. Stateless operators are those operators which does not have any memory of previous events. It can be any transformation operator, for example, multiply by 2 or do some transformation, whereas stateful operators require a history of previous input events, for example, taking an average. Now let's talk about recovery and processing guarantees in a DSPF. A recovery means how a system recovers after a failure. It depends on the type of operators. A stateless operator can simply be restarted, as it does not contain any state, whereas stateful operator requires a bit more thoughtful approach. There are many ways how stateful operators can be restored, for example, replaying state updates or snapshotting the state or using resilient distributed data structures. Processing guarantee means that how a system ensures correctness during failure. There are 3 general processing guarantees that these DSPs claim to provide. First, and the most loosest, is at most once, which means that an input event will be processed at most once, and it is possible that an input event is not processed at all. In comparison, at least once means that any input event will be processed at least once. It may happen that an input event will be processed twice, but no input event will be missed and every input event will be processed at least once. Similarly, exactly once means that any input event will affect the output exactly once. An input event will not be processed more than once, neither it will not be processed. However, these processing guarantees are only applied as far as the data source and the data sink also provide these processing guarantees. Now let's discuss the benchmarking design of our study. First, let's discuss our workload. Our workload counts the number of the time a web resource is accessed in the last 1 minute, and it shows the most accessed web resources. For this, it consumes 2 event streams. One is the click event and the other is update event stream. These two events are first ingested by our topology, and then some transformation is applied. This transform stream is then joined, and then after that it's grouped by the resource. Then a window operator is applied, which counts how many times a resource was accessed in the last 1 minute, which is then forwarded to the egress operator, which sends the record to the sink. Every output event will contain a list of all the input events that are processed to create this output event. We use Apache Kafka as our source and sink. Apache Kafka is a streaming engine in which data can be stored in topics. These topics can be partitioned and replicated on multiple brokers. Apache Kafka also provides data localization, which means that all the events related to one web resource are sent to one broker. Here we show the definitions of our input events, namely click event and the update event. And we use a synthetic dataset so that we can have a controlled output. The data is distributed through a data generator whose throughput can be sorted. And we run all our experiments such that the data generator is operated at the optimum ingestion rate, where optimum ingestion rate, or OIR, is the highest throughput such that the latency remains stable. If we run the data generator higher than OIR, then input events will start to queue and our latency would start to explode. Here we show the architecture of our benchmarking system. We have separated our system under test, or an NADSBF, from our benchmarking utilities. The data generator writes the data to input streams of Kafka cluster, which are then consumed by our system under test, or NADSBF, which processes this input data and produces output. These outputs are written back into Kafka cluster. During this processing, we use Pumbaa to inject failures into our stream processing system, and then we measure the latency and throughput of our system using our benchmarking utilities. Here we show the workflow of our experiments. At T0, we deploy the source and sink, and also deploy the topologies, which makes the topology ready to consume the events. So at T1, we start our data generator, and then at T2, we introduce a failure into our system. And then at T3, we remove the failure from the system. And then at T4, we stop the data generator and we let our system to run until it's finished. Hence, we can say that we divided our experiment into 3 different phases. First is the before fault phase, where our system was working perfectly and there was no failure in our system. And the second phase is the during failure phase, in which there was a failure in the system. And there's a post-failure phase, which is after we have removed the failure from the system. For our study, we have shortlisted 3 widely used and open source stream processing systems, namely Kafka Streams, Apache Storm, and Apache Flink. And the comparative analysis of all 3 systems are summarized in this table shown here, which highlights the architecture and the fault recovery mechanism and the state backend and the processing guarantees of these systems. Now let's have a look at some of the interesting results that we obtained during our benchmarking. Every experiment is accompanied with a latency graph, a throughput graph, and an ingestion rate graph. In the ingestion rate graph, the black line denotes the affected node. In this experiment, we injected process crash into our system at T2, and we see that at T2, the affected node stopped processing. However, its workload was rebalanced to non-affected workloads, which caused higher ingestion rate at the non-affected workload. As soon as at T3, the process crash was removed from the system rebalanced the workload and all the nodes and the machine started working optimally. In this experiment, we saw the latency to have an 81% spike and the throughput drop to be 5%. In this experiment, we saw that it had no at least once processing guarantee. However, it has exactly a once processing guarantee. And similar observations were made when we injected 20% packet loss into our system. However, we saw that in the In the 20% packet loss experiment, the affected node continued processing the stream. However, it failed, but the workload was not transferred or rebalanced to the non-affected load, which caused a high spike into our. We experienced a high spike into our system. We saw a 300% spike in our system, and a higher throughput drop of 30% as compared to 5% in process crash. However, we saw at least once and exactly once processing guaranteed to be fulfilled in this experiment. Another interesting result were obtained when we ran another experiment where we injected 80% packet loss into our system. Intuitively, the results of the 80% packet loss should be worse than the 20% packet loss. However, we saw that our latency was also reduced to 155% as compared to 300% spike, and also the throughput drop was reported to be less. How did this happen? When we look at the graphs, we see that when we injected 80% packet loss, the system treated this failure as a process crash failure, and it redistributed the task of the affected node to the non-affected node, which made the system a bit more performant in this failure. Similar observation can be made in other experiments or in other failures. Similar experiments were also performed at Apache Storm, and here we saw an interesting result that the latency spike in all of these experiments is much less significant than the latency spike we experienced in Kafka Storm. However, the throughput drop was much more significant as compared to Kafka streams. And also, the at least once claim processing guarantee was only possible in 20% packet loss, and the packet delays were less than timeouts. Apache Flink showed interesting results. For example, here we injected process crash into one of the nodes in the system. However, the whole system just stopped processing, even though there were other nodes who were not affected. But even just injecting failure into one of the node in our system, the whole system started processing, and the throughput drop was 100%. However, when we injected partial failure, like we were injecting 20% packet loss, we saw that the throughput drop was minimal, and it still continued processing the system. And similarly, when we injected 80% packet loss, the system still considered as a process crash, and the whole system stopped working, and the whole system stopped producing anything at all. Now, let's try to find out the key insights from our experimentation. We found out that every DSPS has its own strengths and weaknesses. For example, Apache Flink has the lowest latency, and it should be used for time-sensitive applications. Interestingly, Apache Flink halts the whole processing when there's a failure in just only one machine. Even though there are some machines in the system who are not affected by the failure, yet the whole system just stops processing. But the question here is how to fix it. So to make your Apache Flink more fault tolerant, you need to have more redundant work in your system. When you have more redundant work in your system, an affected node's workload can be transferred to the redundant worker, and the system continues to process the streams. For example, here we can see we injected the failure here at T2, but we had a redundant worker. That's why the system still continued processing the stream, and the effect on the throughput is almost negligible here. However, Apache Flink does not offer any processing guarantee. In contrast, Apache Storm has the least impact on latency during failures, and also it handles partial failure much better than other two competitors. For example, it just caused 10% increase in latency as compared to 5 times increase in Kafka Stream and 10 times increase in Apache Flink. And it just only offers at least once processing guarantee only in partial failures. Kafka Stream strikes a good balance between throughput, latency, and correctness, and it is the only DSPS in our benchmarking that provided exactly once processing guarantee. And it also handles process crashes better than partial failures. So if you are facing partial failures in your system, such as like packet loss or some network delays, it is better to kill that process so it's in the failure zone rather than to continue working it in the partial failures. Or just if I summarize my whole talk, it would be this one-liner that the processing guarantees of these distributed processing systems should come with an asterisk, which tells the conditions under which these processing guarantees are maintained. With that, thank you very much, and please feel free to ask any questions.